Good evening, students. So in this video we are going to discuss how drugs like acetazolamide helps in managing mountain sickness, right? For understanding the step-by-step mechanism how acetazolamide helps in managing mountain sickness, first of all we need to understand what actually goes wrong in mountain sickness, right? Suppose someone goes to high altitude, right? So what's the first challenge he is facing? Hypoxia, right? Now this hypoxia will be sensed by the peripheral chemoreceptors, right? Your peripheral chemoreceptors are going to sense this hypoxia. I will draw a box in the center. We will need this box for discussing the mechanism later on, right? Okay, so a person has gone over the mountain and the first challenge he is facing is hypoxia. This less oxygen level is first of all detected by peripheral chemoreceptors, right? Now what it will lead to? It will lead to a hypoxic ventilatory drive, which will lead to hyperventilation, right? So this thing will lead to hyperventilation. Now, suppose someone is hyperventilating, right, breathing a lot. So which gas comes out when we breathe out? Right, CO2, right? So if someone is hyperventilating, it will lead to CO2 washout, right? The CO2 levels are going to decrease, right? The carbon dioxide levels are going to decrease. Now coming back to our 11th and 12th chemistry, right? If you push CO2 into any solution, you make it acidic. And if you pull CO2 out of any solution, you make it alkaline, right? Okay. So what it will lead to? It will lead to respiratory alkalosis. And what respiratory alkalosis means? High bicarbonate levels, right? So this will lead to respiratory alkalosis. And what respiratory alkalosis means? Your bicarbonate levels are very high. Now these high bicarbonate level, right, will send a negative feedback inhibition to your central and peripheral chemoreceptors, right? They will send a negative feedback inhibition to both central and peripheral chemoreceptors. Your central chemoreceptors and peripheral. Right? Up till now, the story is simple, right? First of all, there was hypoxia. This hypoxia was sensed by the peripheral chemoreceptors, which led to a hypoxic ventilatory drive, the hyperventilation, right? This hyperventilation led to CO2 washout, which led to respiratory alkalosis. Now, this respiratory alkalosis has got a negative feedback on peripheral and central chemoreceptors, right? And what this will lead to? This will lead to hypoventilation. This will lead to hypoventilation. But what's the issue here? Right? Why we should be worried about this hypoventilation? Because this hypoventilation is happening while still there is hypoxia. Right? In atmosphere, the pressure of oxygen is still low, and in that low oxygen environment you are hypoventilating. So this is something dangerous, right? In low oxygen environment you are hypoventilating, right? So the dissolved oxygen in the blood, right, is going to reduce drastically, right? So your SaO2, right, is going to reduce drastically. Right? Now, why we should be worried if this SaO2 declines, right? This SaO2 will start a vicious cascade inside the body, right? The two major organs it is going to affect are your brain and your lungs, right? The starting effects of the hypoxia on brain and lungs are exactly opposite, but the ultimate end result is same, edema, right? So in brain it will lead to vasodilation, but in lungs it will lead to vasoconstriction, right? So SaO2, right? SaO2, when it deals with brain, it increases the level of nitric oxide and adenosine. Right? If you follow my previous videos, this adenosine compound, you remember, right? This adenosine causes vasodilation all over the body, but in renal vasculature it causes vasoconstriction, which gives our mechanism of tubuloglomerular feedback, right? So in brain it is going to cause vasodilation, but in kidneys it is going to cause vasoconstriction. Now SaO2 is less, the level of nitric oxide and adenosine is going to increase, right? So what will happen? Suddenly the vessels in the brain have dilated, so more blood will go inside. If more blood goes inside, the volume of the blood will increase, right? If volume of the blood is increased, your cranium has got a limited capacity, right? So intracranial pressure will increase, right? So this thing will lead to vasodilation, and what vasodilation will lead to? Vasodilation will lead to increased cerebral blood flow. Cerebral blood flow is going to increase, right? And if cerebral blood flow increases, your intracranial pressure is going to increase, right? And if intracranial pressure increases, the pressure on those capillaries, on those fragile capillaries, is also going to increase and they will burst, right? So it will ultimately lead to cerebral edema, right? We also call it high altitude cerebral edema. In short form, HACE, right? High altitude cerebral edema. Right? One thing hypoxia can also do is that it is going to secrete lot of reactive oxygen species, right? And also cytokines and interleukins, TNF alpha, interleukin 6, right? All these will cause damage to blood-brain barrier, right? All these will cause damage to blood-brain barrier. Now, if damage to blood-brain barrier happens, right, what will happen? Again, the cerebral edema happens, right? One more thing SaO2 can do is that it can the supply of this sodium potassium ATPase pump, right? Sodium potassium ATPase pump will get inhibited, right? If sodium potassium ATPase pump get inhibited, right, of course the cell are going to swell, right? You know, the sodium potassium ATPase pump, it pumps 3 sodium outside, 2 potassium inside. If that gets inhibited, lot of sodium will get accumulated inside the cell. If sodium comes, the water will follow and your cell is going to swell up, right? And this will further lead to your cerebral edema, right? This will lead to cell swelling and cerebral edema, right? And this will lead to again cerebral edema. So the multitude of factors. Once the SCO2 level falls, the level of nitric oxide and adenosine is going to increase, right? If nitric oxide and adenosine level increases, it will lead to cerebral vasodilation, more blood flow, more volume of blood flow, right? If the blood flow increases, the cranium cavity has got limited space, it will lead to increase intracranial pressure, which will further lead to cerebral edema. All the reactive oxygen species will further damage your blood-brain barrier, leading to cerebral edema. Low oxygen level will also inhibit your sodium potassium ATPase pump, which will lead to cell swelling and edema, right? Now what happens in lungs, right? In lungs, this low oxygen level does the opposite. It leads to pulmonary vasoconstriction. Now how it leads to pulmonary vasoconstriction, right? These potassium ion channels inside lungs, they are very sensitive to oxygen levels, right? So once the oxygen levels falls, these potassium ion pumps get inhibited, and this leads to depolarization of the cell. Why depolarization of the cell? Because these potassium ion channels are transporting potassium out of the cell. If this ion channel get inhibited, the potassium will start accumulating inside the cell, right? So inside will become positive. This will lead to depolarization. This is going to open your voltage sensitive calcium channels, right? And which will ultimately lead to pulmonary vasoconstriction, right? If pulmonary vasoconstriction happens, right, it will increase your pulmonary arterial pressure, right, which will further increase the pulmonary capillary pressure, and these capillaries will burst, right? And you will ultimately get pulmonary edema, right? So just in case you get less SaO2, right, it will lead to depolarization. Why depolarization? Because the potassium ion channels will be blocked, right? These potassium ion channels will be blocked, so you get a lot of potassium inside the cell, right? Depolarization of the cell is going to open up the calcium ion channels. The calcium will enter inside, which will lead to vasoconstriction, pulmonary vasoconstriction, right? And this vasoconstriction what it will do? This vasoconstriction is going to increase the pulmonary atrial pressure, right? And if it increases the pulmonary atrial pressure, it will further increase the pulmonary capillary pressure, right? And if it increases the pulmonary capillary pressure, ultimately it will lead to pulmonary edema, right? So there are two complications, and both are life-threatening complications. Right? So there are two complications, and both are life-threatening complications. One is cerebral edema, and one is pulmonary edema. Right? We also call it high altitude pulmonary edema, HAPE. Right? So you can see this cascade, right? How in physiology one thing leads to another, right? It starts with something, it leads to other thing, it leads to another thing, and once you understand the sequence, it will help you in understanding so many other disorders also, right? So it started with which thing? It started with hypoxia. What hypoxia led to? The hypoxia led to the detection by the peripheral chemoreceptors, which led to hypoxic ventilatory drive. Hypoxic ventilatory drive, hyperventilation, the CO2 was washed out, right? Since the CO2 got washed out, it led to respiratory alkalosis, which means high bicarbonate level. This led to feedback, the feedback inhibition of your peripheral and central chemoreceptors, right? Now person is hypoventilating in hypoxia. Now hypoventilating in hypoxia is something dangerous, right? So this will lead to drop in your dissolved oxygen levels, right? This will increase the level of nitric oxide and adenosine. This will lead to vasodilation. More blood will rush inside the brain, but the cranial cavity has got limited space, right? So it will increase your intracranial pressure, increase the pressure on those capillaries, ultimately leading to cerebral edema. These reactive oxygen species will damage your blood-brain barrier, ultimately leading to cerebral edema. Hypoxia is going to inhibit your sodium-potassium ATPase pump, leading to cell swelling, ultimately leading to cerebral edema, right? Now this SaO2, less SaO2 is going to inhibit the oxygen-sensitive potassium ion channels in lungs, right? So the potassium won't go out, leading to depolarization of the cell, right? Which is going to open the voltage-sensitive calcium ion channel, right? Since the voltage-sensitive calcium ion channels, it will lead to pulmonary vasoconstriction. Pulmonary vasoconstriction will lead to increase in pulmonary arterial pressure, which will increase the pulmonary capillary pressure, right? Which will lead to pulmonary edema, right? So both cerebral edema and pulmonary edema are life-threatening complications, right? Now, as a doctor, we need to understand how the drugs like acetazolamide, right? How it helps in managing, right? How it helps in managing the effects of mountain sickness, right? So what's our main problem over here? Which thing actually created the cascade? These high bicarbonate levels actually created the whole cascade. Now we somehow need to get rid of this high bicarbonate level to prevent this cascade, this whole deleterious cascade from happening. We need to somehow get rid of this high bicarbonate levels. For that, we need to understand how exactly the bicarbonate is absorbed in PCT, right? For understanding that, we need to draw a cell of PCT first of all, right? First of all, let's draw a cell of PCT, right? This is the basolateral side and this is the luminal side, right? Now, on the basolateral side, we have got our main hero. Who is our main hero? Sodium potassium pump. It is pumping sodium outside and it is pumping potassium inside, right? If it pumps sodium outside, what will happen over here? The sodium is going to decrease. Sodium is going to decrease over here. If sodium decreases over here, from the luminal side, we will get a gradient. So sodium will come out, right? But H plus will go out. H plus will go out, right? Now from where this H plus is coming, right? For understanding from where this H plus is coming, we need to draw a chemical reaction, right? The CO2 is combining with water, right? The CO2 is combining with water and this thing gives rise to H2CO3. This H2CO3 is breaking into H plus and HCO3 minus, right? Now, this HCO3 minus goes out, right? And chlorine comes in exchange of that through bicarbonate chloride antiporter, right? Now, the main thing, the R bicarbonate, right? This bicarbonate combines with this H plus ion and forms H2CO3, right? And this H2CO3 breaks down into H2O plus CO2 and this H2O plus CO2 goes inside, right? So through this cycle, the bicarbonate is actually absorbed, right? So this bicarbonate is actually the same bicarbonate which you find over here, but it's not getting absorbed directly, it's getting absorbed indirectly. It is combining with this H plus, forming H2CO3, breaking down into H2O plus CO2. This CO2 plus H2O goes inside, again combines into H2CO3, which breaks down into H plus and bicarbonate, and this bicarbonate goes outside. So this bicarbonate is the same bicarbonate which you're seeing over here, which gets absorbed indirectly, right? And we need to somehow break this chain. We want this bicarbonate to actually go out, right? We don't want this bicarbonate to be reabsorbed. So somehow we need to break this chain of reaction, right? So how this will happen, right? For this, we need to understand one enzyme, right? Carbonic anhydrase, right? CA we will write in short form. This carbonic anhydrase catalyzes both these steps, right? We have got a cellular carbonic anhydrase which catalyzes this step, CO2 plus H2 into H2CO3. We have got a luminal carbonic anhydrase which catalyzes this steps, which breaks down H2CO3 into H2O plus CO2. So carbonic anhydrase is required for both these steps, right? Now somehow if we inhibit this carbonic anhydrase, then what will happen? This CO2 and H2O won't combine to form H2CO3. So this H plus ion won't be generated. If this H plus ion is not generated, it is not going to combine with bicarbonate, and this bicarbonate will be straight away excreted out, right? So we need a drug to inhibit this carbonic anhydrase, and that drug is our acetazolamide, right? Acetazolamide. Right? So acetazolamide is going to inhibit carbonic anhydrase, right? So if we see the chain reaction, how acetazolamide helps in curing mountain sickness, acetazolamide is going to inhibit carbonic anhydrase, right? If carbonic anhydrase is inhibited, CO2 and H2O won't combine to form H2CO3, right? This H plus won't be generated, this H plus won't go out, it will not combine with this HCO3 minus. This HCO3 minus will be straight away excreted out, and this is exactly what we want. If this HCO3 minus gets excreted out, you won't have the high level of bicarbonate over here. If you don't have high level of bicarbonate over here, you will no longer have this negative feedback inhibition of peripheral and central chemoreceptor. So you won't have hypoventilation, right? Apart from that, if you see, if this thing, right, if bicarbonate goes out, right, then you will also have more H plus inside the body, right? If this whole bicarbonate gets washed out, right, you will have more H plus inside the body. If this bicarbonate gets washed out, you will also have more chlorine inside the body. So this acetazolamide will lead to what we call hyperchloremic metabolic acidosis, right? Hyperchloremic metabolic acidosis. Now this metabolic acidosis will stimulate ventilation, right? It is going to inhibit your hypoventilation. It is going to stimulate, it will lead to hyperventilation, right? Okay, so it is going to, when it stimulates your ventilation, it is going to improve the level of SaO2, and all this deleterious cascade will be obliterated, right? One thing also acetazolamide does is that it reduces the synthesis, the CSF synthesis, right? When the CSF synthesis is reduced, when CSF secretion is reduced, right, this will also inhibit your cerebral edema, right? So acetazolamide will block this step, right? It will lead to excretion of bicarbonate ion, which is going to increase the H plus ion inside the body, which will lead to hyperchloremic metabolic acidosis. Due to less bicarbonate ion, this negative feedback inhibition of peripheral chemoreceptors won't be there. Due to metabolic acidosis, you will have hyperventilation. The ventilation will be stimulated. So this step of hypoventilation will be inhibited, right? And all this deleterious cascade of cerebral edema and pulmonary edema won't be there, right? So let's sum it up. What actually goes wrong in mountain sickness, right? First you get hypoxia. This hypoxia is sensed by your peripheral chemoreceptors, right? These peripheral chemoreceptors stimulate the ventilation. It leads to hypoxic ventilatory drive, the hyperventilation. The hyperventilation washes out the CO2, right? Washing out of CO2 leads to respiratory alkalosis. Respiratory alkalosis means high bicarbonate level. This high bicarbonate level leads to feedback inhibition of your central and peripheral chemoreceptors, right? Since there is feedback inhibitions of peripheral and central chemoreceptors, right, this will lead to hypoventilation. Now, hypoventilating when still there is hypoxia is something dangerous. So your dissolved oxygen level, the SaO2 level, will go down. This will start a cascade reaction both in your brain and lungs. In brain, it will increase the level of nitric oxide and adenosine, which will lead to cerebral vasodilation. More blood will rush in, blood volume will increase in a limited cranial cavity, right? So your intracranial pressure is going to increase. Since the intracranial pressure is increased, it will put pressure on your capillaries, leading to cerebral edema. All the reactive oxygen species, cytokines and interleukins will damage your blood-brain barrier. This will also lead to cerebral edema, right? It will also inhibit your sodium potassium ATPase pump, right? This will lead to cell swelling and cerebral edema. Low SaO2 level will inhibit the oxygen sensitive potassium ion channel in your pulmonary vasculature, right? So this potassium will get accumulated inside, leading to depolarization. The calcium will come inside, right, leading to vasoconstriction. Vasoconstriction means high pulmonary atrial pressure. High pulmonary atrial pressure means high pulmonary capillary pressure, ultimately leading to pulmonary edema, right? So now our real hero will walk in. Our real hero over here is acetazolamide, right? What acetazolamide is going to do? It is going to block this step, which converts CO2 plus water into H2CO3, and also this step, H2CO3 into H2O plus CO2. So this H plus won't be excreted out. So this H plus won't combine with HCO3 minus. So this HCO3 minus will be excreted out. If this level of HCO3 falls, you won't have the negative feedback inhibitions on peripheral and central chemoreceptors, right? And if this bicarbonate gets excreted out, you will have a lot more H plus ion. To be exact, hyperchloremic metabolic acidosis. This H plus ion is going to stimulate your ventilation and will improve the level of SaO2, which will break this deleterious cascade of cerebral and pulmonary edema, right? So hopefully this video has helped you in understanding how acetazolamide helps in managing your mountain sickness. Wish you all the very best. Thank you.